Hi everyone. In this video we're going to continue our discussion on alpha carbon chemistry. So the next reaction we're covering is Claisen condensation. So in this reaction we're using an ester instead of a ketone or an aldehyde. So let's say we have the following ester. So we've got an ethoxy group attached there. That's our ester leaving group. And we're going to react this with a base. And the base is going to be an alkoxide ion. Now notice that in particular I drew an alkoxide ion that matches our ester leaving group. And that's really important for this Claisen condensation reaction. So let's just make a note. The alkoxide base should be the same as the ester leaving group. And we'll talk about why that is in a second. The second step in this reaction, we're just going to add an acid. We'll also talk about why we need an acid there on the next slide. So what we end up forming is something called a beta keto ester. So notice we have our new bond between the alpha and beta carbons. And on the beta carbon, we have a ketone. But we've also still kept our ester from before, so that's why this is called a beta keto ester. Okay, so why do we have to use an alkoxide base that matches our ester leaving group? Why can't we use a hydroxide ion, for example? So if we used an OH group, then we would end up forming a carboxylic acid. So that wouldn't give us the beta keto ester that we're trying to produce in this case. Well, what if we use a different alkoxide ion? Like instead of the ethoxy group, what if we used methoxy or methoxide base? Oh, I was trying to combine my words. There we go. So if we used a different alkoxide, then we would perform transesterification. And remember, in transesterification, we're basically turning one ester into a different ester. So we would just replace that ethoxide group with a methoxide group, for instance. And we would not end up with our beta keto ester. So for this Claisen condensation reaction, again, it's really important that the alkoxide base is the same as the ester leaving group. And that will give us that final desired beta keto ester. So let's look at the mechanism for this reaction. So let's start with our same ester. Oop, forgot the oxygen there. And again, this is going to involve alpha protons. So I'll just draw those on here. And like we saw earlier, we're going to react this with our alkoxide base that matches our leaving group. And that alkoxide base is going to deprotonate the ester, and we'll leave electrons behind on our alpha carbon there. You could also draw the resonant structure where you form a pi bond between those two carbons and then move electrons up to oxygen, but this is probably quicker just to show the electrons sticking to the carbon. All right, so now we formed an enolate, which this looks very similar to previous reactions that we've looked at in this chapter. So now that enolate is going to attack oops, the same ester that we had before. So this is just another ester molecule that's in solution. And we're going to attack the carbonyl carbon. And that's going to give us the following. So on that beta carbon, we have a negative oxygen, we have a good leaving group, and then we have our methyl group. So what we can do is reform our double bond between oxygen and carbon and kick out our leaving group. All right, so it looks like we formed our beta keto ester. However, unfortunately, we can't stop here. So the alpha carbon that sits between our two carbonyl groups has very acidic protons on it. Oops, started spelling the wrong word there. Acidic. Now, why are those protons so acidic? Well, remember, if we look at the conjugate base, there are two carbonyl groups, so we can form two resonant structures on the conjugate base, which means the conjugate base is super stable, and that's going to make the original proton that was there very acidic. So we do have our ethoxide ion hanging around from the previous step. That was our leaving group. So that can then deprotonate our beta keto ester. So then we'll have a negative charge on that alpha carbon, and that's why in our last step we have to use some acid to reprotonate the beta keto ester. Whoa, I drew a really big oxygen there. And then one of our byproducts is the conjugate acid of our alkoxide base. So in this case, we formed ethanol. And we could probably just use the difference in physical properties to boil off the ethanol or remove it in some way. All right. Now, similar to our aldol reactions, where we could also perform crossed aldol reactions, we can perform crossed Claisen condensation. So this is going to involve combining one ester with one enolizable ketone or ester or aldehyde. Oh, I misspelled aldehyde, but you know what I mean. So let's look at an example. So I'm going to draw an ester, and let's say we already formed an enolate, and let's say we're using a ketone. So we'll just use acetone here, and let's say we already removed one of its alpha protons. So now it's an enolate. Also notice that our ester doesn't have any alpha protons, so that can't be our enolate, and we're kind of controlling which starting material is our enolate, similar to our crossed aldol reactions. So now we're going to use our alkoxide base, which should match our ester leaving group. And then in the last step, we're going to protonate the alpha carbon, because remember, those protons are really acidic, so we want to add that back in at the end. So what we do is basically just combine the two starting materials and get rid of the ester leaving group. So pretty easy there. So again, sometimes with these crossed reactions where you have a mixture of starting materials, you'll end up with a mixture of products too, and it gets kind of annoying to have to separate all those different products. So if you can control the products that you end up with, it's much easier. So for instance, one way that we can control this reaction, similar to the crossed aldol reaction, is to make sure that one of your starting materials doesn't have any alpha protons. If it does, what you can do instead is add the starting material that you want to be the enolate into LDA and then transfer it to the second starting material. So let's just write that down. So if both starting materials have alpha protons, then first add the starting material you want to be the enolate. So the starting material that you want to have a negative charge on into LDA. So remember, that's the base we can use to pull an alpha proton off of our ketone or aldehyde, etc. Then transfer the enolate to the second starting material. So just a technique we can use to kind of control what products we end up with. Now let's look at a different situation. So let's look at a challenge problem. What if we have the following? And we're going to react this with the alkoxide base that matches the leaving group, and then acid. So I want you to pause the video and try to figure out what the product is on your own first. Now, I'll give you a couple hints. This is going to be an intramolecular reaction. And the product is a ring system. So see if you can figure out the product there, and when you're done, you can unpause the video and we'll go over it together. All right. So in the first step, normally we would deprotonate the alpha carbon on our ester. So it doesn't really matter which ester here we take a proton from because it's a symmetrical molecule. So let's just take a proton from the alpha carbon on the right. So it's just kind of an arbitrary thing. And we're going to leave electrons behind on the alpha carbon. All right, so we formed our enolate on the right-hand side, and we have our other ester on the left-hand side. So now that enolate can attack the ester, and we'll move electrons up to oxygen. And again, we're attacking the carbonyl carbon there. So this is where we have our intramolecular reaction, and we're starting to form a ring. So let's count the carbons that would be in our ring. So we've got 1, 2, 3, 4, 5. All right, so that means we're forming a 5-membered ring. And they're all carbons, so that makes it a little easier. So I'm just going to number the carbons in the ring I just drew, and then I'm going to reference my previous drawing to figure out what is on each carbon. So on carbon 1, we have our ester. So let's draw the ester there. And on carbon 5, we have, let's see, we're going to have a negatively charged oxygen and then our ethoxide group as well. Oh, whoops, I drew that on the wrong side. I mean, it doesn't really matter because it's symmetrical, but we'll just stay consistent. All right, so we've got a negatively charged oxygen and then our ethoxide group. Now, what's great here is that the ethoxide group is a good leaving group. So we can form a double bond with our negatively charged oxygen and then kick out that ethoxide group. All right, so now we have a ketone and an ester. So let's try to find our alpha carbon here, because remember, this is our beta keto ester, but the protons on the alpha carbon are very acidic. So the carbon that's in between these two carbonyl groups, that's our alpha carbon, and there is in fact one proton on that carbon. So the ethoxide group that just left our molecule, that can grab our acidic proton, and then we'll just leave electrons behind on the alpha carbon. Let's see. Oh, I'm running out of room. Let's see if I can fit this in here. All right, so we've got a negative charge on that carbon. So in the last step, we're just going to react that with acid to reprotonate that. And we end up with, ooh, I can draw a better 5-membered ring there. That was a little rough. That's a little better. And now we have our final product. So we've got our beta keto ester. And this was all formed using one molecule. Okay, so let's summarize everything we learned in this video. So we said that Claisen condensation is going to give us 2 carbonyl groups on our final product. So Claisen condensation is good for forming dicarbonyls. So that's where we have those 2 carbonyl groups. And they're attached on either side to something. It kind of depends on what you're using. Now, let's compare this to aldol addition or condensation. Oh my gosh, I'm writing like diagonally up the page. It's hard to draw or write in straight lines on an iPad. So if we performed aldol addition or aldol condensation, we would end up forming a carbonyl group and an alcohol, or a carbonyl group and an alkene. So we would be forming a beta hydroxy group or an alpha beta unsaturated, carbonyl. So we might form this beta hydroxy situation, or a situation here where we've got a carbonyl group and an alkene. Okay, so both reactions are really useful. It just kind of depends on what you're trying to form. This might be part of a synthesis problem, or maybe this is just the final product you're trying to get to. Either way, we have these new tools in our tool belt, and we can form either dicarbonyls or a beta hydroxy carbonyl or an alpha beta unsaturated carbonyl. All right, so now in the next video, we're going to discuss alkylation at the alpha position. So we'll be able to add carbon groups to the alpha position. So I will see you then.